In the last video, we looked at the problem that Grover's algorithm solves in classical terms. And that problem is, given some function f of x, find the special value of x star, such that f of x star is equal to 1. In this video, I want to look at the quantum computing version of this problem. The first difference is that quantum computing deals with vectors and not numbers. So the inputs to this function are going to be vectors instead of numbers. So x turns into the basis vector x. And f is no longer a function, but a linear transformation that turns vectors into other vectors. So I'll denote this by the linear transformation O, which stands for oracle. It gets its name from the oracles of classical antiquity, by the way. The straightforward translation from the function f to the linear transformation O would be to have O acting on the basis vector x equal to the basis vector 0 if x is not equal to x star, and to have O acting on the basis vector x star equal to the basis vector 1. This doesn't work because it means the linear transformation O is non-invertible. If we know the output of O acting on some basis vector is the basis vector 0, then there's no way to figure out what the input vector was. It could have been any of the basis vectors besides the basis vector x star. And in a previous video, we said any linear transformation acting on a qubit has to be invertible. This is just the way quantum mechanics works. So here's an alternative way to define O such that it is invertible. We have the result of O acting on any basis vector x not equal to the basis vector x star, just equal to that vector itself. And the result of applying O to the basis vector x star is negative x star. So we just negate the amplitude. If we want to write this more compactly as a single expression of what O does to all basis vectors, rather than having two cases, we can reintroduce the function f from the previous video. Note that in the first instance, the amplitude of the basis vector x can be written as -1 to the 0, because this is equal to 1. And f of x for all x not equal to x star is also equal to 0. So we can write this amplitude as -1 to f of x. For the special case of the basis vector being x star, we can write the amplitude as -1 to the first power, because this is just -1. And f of x star is also equal to 1, so we can additionally write this as -1 to the f of x star. So a single expression that captures both of these cases is just writing the amplitude as -1 to the f of x. So we've defined the behavior of O on all basis vectors. And because O is a linear transformation, this is equivalent to defining the behavior of O on all vectors. So O acting on a linear combination of two basis vectors, say a1 times x1 plus a2 times x2, is just equal to O acting on each of these individually and then summing the result. So the quantum version of the problem we talked about last time is, given this linear transformation O, the oracle, find the vector x star such that O acting on x star is equal to negative x star. And this is the actual problem that Grover's algorithm solves.